We're now going to start the thermochemistry unit. This is part one of the first set of notes. Thermochemistry is basically looking at the energy changes that are involved whenever you carry out a chemical process. So, for example, when you dissolve something, when you combust something, physical processes can be included in this as well, such as changing state, melting, boiling, that sort of thing. And so looking at the energy changes that are involved, whether the system is absorbing energy or releasing energy in the process, that's all under the thermochemistry umbrella. So what's energy? Those of you taking the physics, you know that energy is simply the ability to do work. We get energy from various sources, chemical reactions, solar energy, nuclear energy, geothermal energy, etc., etc. That energy then has to be converted into a different form, either for something useful, or if it's not useful, that's generally in the form of heat. Energy conversions are a big part of this. So, for example, converting nuclear energy to heat energy, to steam, which is a physical change, and then to electrical energy. Those are all energy conversions. The physics tends to look at these processes and how it works. For us, we're going to look at how that affects chemical reactions and how do we start to include that information when we're dealing with chemical reactions, because that becomes kind of important sometimes. We measure energy in joules. The old units are calories, hence the term calorimeter. We're going to be using some of those devices. Well, we would be if we were in a lab. But that's the old imperial unit. You will still see that sometimes, but not so much anymore. All right, the two main types of energy fall under the category of kinetic energy, which is the energy of motion, and then secondly, the potential energy, which is stored energy. We're going to be using both of these. The kinetic molecular theory is the kind of guiding rules that we set out for understanding what's going on in terms of the behavior of the particles, atoms, molecules, ions, etc. So the first idea here is that all matter is made up of tiny particles. We've talked about that once before. These particles are always in constant motion, that is, they have kinetic energy. The particles of matter have spaces between them. The speed and spacing of the particles determine the state of the matter. Adding heat or energy increases the speed of the particles and increases their average kinetic energy. It also changes the spacing between them. So when you increase the kinetic energy, they necessarily have to have more space between them. So what do we use temperature for? Temperature is that measure that we use for the average kinetic energy of a substance. So the higher the temperature, the higher the average kinetic energy, and the larger the spaces between them. We use change in temperature as our delta T. That's the symbol we use, always capital T. So delta T is simply the final temperature minus the initial temperature. The heat that we add or remove from a system is simply the amount of energy that we transfer in or out. So if you have, for example, a hot steel bar, then it has an awful lot of kinetic energy to it. You place that in cold water, well, the heat has to transfer somewhere. So it transfers into the water. You'll notice the big whoosh of steam. Well, that's what happens is because we've transferred the energy from the really hot bar, then it goes into the water, which is at a lower temperature, and so therefore lower kinetic energy. And so the energy always flows from a concentration of high energy to a concentration of low energy. The law of conservation of energy, or the first law of thermodynamics, which is also what it's called, simply says that energy cannot be created or destroyed, but it can be transferred from one object to another, or we can convert it into one form or another. So we look at two things when we're studying energy changes. We first of all look at the system, that is that part of the universe that you're studying, looking at this in specific details, and the surroundings, and that's everything else in the universe. And it's really, really important that you be able to separate what is system and what is surroundings whenever you're dealing with energy changes. Getting that mixed up kind of gives you kind of weird results, and so that's really, really important that you be able to understand what is the system, what is the surroundings. So any energy change in the system essentially has an equal and opposite change in the surroundings. So that is the delta E of the system is equal to the negative delta E of the surroundings. Any change in the energy of the system has an opposite change in the surroundings. So if you increase the energy of the system, you decrease the energy of the surroundings. These are just a couple of ways to give us that information using delta E or Q. Q is also the symbol that we quite often use for heat. All right, so how do we describe a system? Well, we've got three kinds of systems that we generally deal with. The first one is an open system, and this is where we can exchange matter and energy freely between the system and the surroundings. An open flask with a reaction taking place, for example. This is the kind of thing that we're generally used to. Secondly, we can have a closed system. And this is a system where the matter is confined to a container of some sort, but it's not insulated, and so the energy is free to be transferred to the surroundings and back again. So if you have a stoppered flask, for example, you've got a reaction taking place, you're not letting any gases out, the reaction's taking place inside. However, let's say it feels warm to the touch, so energy is allowed to escape from the flask. And then lastly, we have an isolated system, and that's where you have a situation where neither energy nor matter can be exchanged with the surroundings. And so this is the sort of thing where you have an insulated flask. I didn't write that down. The flow of heat is almost always taking place from an area of high concentration to an area of low concentration. And in a simple situation, this is where you have heat flow from one object to another, and that causes a change in temperature of that which was at the lower energy level. We use a flow diagram to kind of show this sort of thing. The equation that we use is Q equals mc delta T. So the amount of energy is equal to the mass times the specific heat capacity. And let's go through these. Q is the quantity of heat flowing into or out of the system. M is the mass of the substance. The lowercase c is the specific heat capacity of that particular substance. And there's a table that we can look up which has this already worked out for us. And then delta T, of course, is the change in the temperature. So fairly straightforward. Those of you taking the physics before recognize this equation. You've seen this before. Now, how do we apply it? Let's just go back to the definition. Specific heat capacity. For those of you who haven't taken the physics, specific heat capacity is a property of a substance, and every substance is a little bit different, which gives you the amount of energy that's required to change 1 gram of the sample by 1 degree Celsius. So that amount of heat is what we call the specific heat capacity. And it's important that we keep these units fairly constant. All right, so for example, for water, specific heat capacity is 4.18 joules per gram degree Celsius. And what you will realize over some practice is this is actually a fairly large number. It takes a fair bit of heat to get water 1 gram of water to raise its temperature by 1 degree Celsius. Now, that's the specific heat capacity. Heat capacity is not related to a specific quantity of the substance. It's whatever you happen to have, the amount of energy that's used to change that object or material that you have by 1 degree Celsius. That is just the heat capacity. Okay? And it's important that you don't confuse those two ideas. They're related, yes, but specific heat capacity relates to a 1 gram sample, changing temperature by 1 degree Celsius. Heat capacity is any amount of that substance. All right, so let's do this example. How much energy is needed to raise the temperature of 250 grams of water from 20 degrees Celsius to 85 degrees Celsius? All right, so I put the decimal place in here, 3 seconds. All right. Okay, so here we go. Solution. We're going to use our Q equals mc delta T. Change in temperature, 65 degrees, yes. So 250 times the specific heat capacity of water times the 65 degrees works out to 68 kilojoules. Okay. Again, remember from grade 11 stuff, you're needing to watch your significant digits here. Right? So all that stuff comes back into play. Temperatures were to 2 decimal places, even though this was to 3. We want to make sure that we round to 2 decimal places. Right, another example, 2.5 liter container of water at 22.3 degrees Celsius supplied with 20 kilojoules of energy. What's the final temperature? So we can figure out our change in temperature then. Remember, this is the final minus the initial. Using grams, not kilograms. Okay, so we get 20,000 joules divided by 2,500 grams times the specific heat capacity, and that'll give us our change in temperature, which happens to be 1.9 degrees Celsius. Now, we started with 22.3 degrees Celsius. What's the final temperature going to be? Well, this is now a situation where you're supplying water with energy. So therefore, the water, being the system here, is increasing in energy. So is the temperature going to go up or down? That's right, it's going to go up. So that means that this is our final temperature. We're looking for, so this is our initial temperature. We're looking for our final temperature. Okay, so TF minus TI, right? So TF is going to be delta T plus TI, and so that's going to be 24.2 degrees. Okay, so always important to make sure that you understand, okay, what's happening to the system? Is it gaining energy? Is it losing energy? All right, and so make sure that you're, like when you're working out these delta T's or initial final temperature, make sure you're looking for the correct one. That can be confusing. It's not usually. This is a fairly straightforward example. And I specifically said here in the question, what's the final temperature? But that's not always the case. Okay. Signs are important. That's going to play a bigger role later on in some of the questions that you're going to come across. All right. So this is a good hour's work. After the note, try these 10 questions. I will post some more stuff tomorrow.